Hello, everyone. Welcome back to the Galaxies Science Interest Group's seminar series. We are kicking start our 2025 to 2026 seminar series. We'll have our seminar talk on the first Wednesday every week. We move our time to 1 p.m. Eastern, and that's 10 a.m. West Coast time. So hopefully you guys all get to join us for the rest of the year. And we still have a few open slots, especially we're opening up the third Wednesday of the week for what we call the fill as we go slot. So if you have timely results, exciting new papers that you're putting out, and you want to use this platform to share with the community, please reach out to me and Benny. All talks will be recorded and posted on YouTube for future references. So it's a great opportunity to have your talk make available to the community. So Benny, you don't have your voice, so I guess I'm just going to do the rest. So today we're going to hear from Erin Kado-Fong. So instead of doing this boring introduction that I do the talking, actually I'm going to make Erin do the talking. I have these two short questions prepared for Erin, but let me start with the first one. So Erin, tell us a little bit about your academic journey. How did you get to where you are now? When did you start?
Yeah.
Yeah.
Yeah. So I actually grew up in California in Davis, and then I moved to the East Coast where I was for almost 12 years. So I moved for undergraduate to do physics at Tufts. I remember when I was thinking about which area of physics that I wanted to do, I was thinking, well, I don't want to be in a lab. So what's the subdivision of physics where everything is so far away that I'll never have to be in a lab? And that's kind of how I ended up in astronomy and astrophysics. Um, During my undergraduate, I started doing research in both uh, stars and the pan-STARRS survey, so kind of large-scale survey astronomy, as well as um, high redshift galaxies. And that really starts or kind of sparked my interest in galaxy surveys, which is still what I work on today. So after undergraduate, I went to Princeton to do my PhD. Part of the reason why I chose the department was because Princeton has such a strong tradition of these wide field surveys, like SDSS. At the time, HSC was wrapping up when I started. Of course, looking forward to LSST. At Princeton, I got really interested in dwarf galaxies in particular, so low mass galaxies, really because they're at this nice kind of intersection between emerging observational capacity. So I'll talk a little bit about this in my talk, but dwarf galaxies are really kind of at our observational frontier because they are such low mass faint systems. And they're also very key systems to answering kind of our fundamental questions, both about baryonic physics and dark matter. So I started getting really interested in dwarf galaxies while I was a graduate student. I then continued on to a postdoc at Yale, where I thought largely about baryonic processes and feedback in dwarf galaxies and how we really need to understand feedback in order to use these systems to probe dark matter. And then very recently, I moved to a another postdoc at Stanford, where I've been thinking more about dwarf galaxies at the intersection of baryonic physics and dark matter.
Awesome. Well, thank you for introducing yourself for us. And I'll let you take the floor and tell us about your galaxies.
Okay, great. Sorry, was there a second question?
We kind of answered it already. It was about how you
Okay.
came into contact with the topic you're currently working on and what got you interested. So I guess if you have more to say,
Oh,
feel
no,
free.
I think I covered it.
Yeah, you
Okay,
did.
let me go ahead and share my screen then.
Yes.
Okay, let me just, sorry, one second. Let me
Yep.
move myself out of the way. And can everybody see my screen?
Yes, I can. The whole thing. Yes.
Okay, perfect.
Great.
Right. So, as I kind of already introduced, I'm mostly going to be talking today about disentangling baryonic and dark matter physics with the smallest galaxies. This is work that I've done both at Yale and Stanford. The the bulk of the work I think was done at Yale, but I'm very excited to continue thinking about these topics at Stanford. Okay, so before I jump into what I've really been doing, I wanted to take a minute to talk about why we care specifically about dwarf galaxies. Oftentimes, for broader audiences, I also have an intro slide that's more like, why do we care about galaxies at large? I think for the galaxies special interest group, I don't need that introductory slide, but I will try to convince you that dwarf galaxies are a particularly interesting class of galaxies, both from the observational and the physics-based perspective. So many of our challenges to lambda-cold dark matter are really strongest in the dwarf galaxy regime. And here I'm showing a really an adaptation of a really nice schematic that was published a couple years ago by Laura Salas, looking at different challenges to lambda CDM, how they manifest in dwarf galaxies, and kind of the state of the field in terms of how resolved or how unresolved these challenges are. So before I get into those challenges, though, I want to just define what I mean by dwarf galaxies. So everybody here thinks about galaxies on the day-to-day, but even if you just talk to people who work on dwarf galaxies, the mass range that they mean when they say dwarf can be different by a factor of 1,000 easily. So I want to be clear first that when I say dwarf galaxy, what I generally mean are stellar mass or halo masses less than around 10% of the Milky Way. So stellar masses less than a few times 10 to the 9 solar masses, or halo mass less than around 10 to the 11 solar masses. So really the most massive thing that I would call dwarf or dwarfish would be the LMC. And then today we're going to be focusing really on classical or bright dwarfs. So these are things with stellar masses between 10 to the 7 to around 5 times 10 to the 9 solar masses. So you can think of the range as something like maybe 10% SNC stellar mass up to around LMC stellar mass. So when I talk about dwarf galaxies, I'm not really thinking about the ultra faints, the kind of 100 solar mass galaxies that some people are really interested in today. Okay, so now that we're on the same page about what a dwarf galaxy is, let's think about how they can be used to probe our understanding of dark matter physics. So in this schematic, you can see some of the most classical or textbook, I should say, small scale challenges to lambda CDM. So these are things like the missing satellites problem, the core cusp problem, the too big to fail problem. And you can also see some new challenges that have emerged over the recent years. And one thing that really ties a lot of the solutions that have been proposed to these challenges together is the importance of baryonic feedback in these dwarf galaxies. So some of these solutions can be baryonic processes that modulate galaxy formation efficiency. So a classic example is baryonic feedback to really solve the missing satellite problem. This galaxy formation efficiency modulation by baryons is also very important in solutions to things like changes in the stellar to halo mass relation, the quiescent fraction of dwarf galaxies. And you can also find a lot of solutions that invoke baryonic processes to change the galaxy and halo structure. So I think the most textbook example of this is the core cusp problem. So using baryonic feedback to indirectly redistribute the dark matter density profiles into cores. But it's also important for proposed solutions to things like dwarf size diversity, rotation curve diversity, too big to fail. So this is great in terms of really trying to solve or answer challenges to lambda-cold dark matter. But one of the problems is that baryonic processes and the whole class of baryonic physics, especially as they operate in dwarf galaxies, our picture is also highly incomplete, and they're very complex processes in and of themselves. So even this schematic, so I'm showing a schematic of kind of general bins of baryonic processes in dwarf galaxies at different scales. Even this schematic, as kind of text heavy and complex as it is still incomplete, is still very broad. But you can think of baryonic processes as operating on different scales. So things like star formation and baryon cycling within galaxies at left. So this can be things like gas flows in the interstellar and intergalactic medium, star formation efficiency and star formation efficiency modulations across galactic environments. You can go out to the kind of galaxy and galaxy halo interface scale and think about baryonic feedback and individual dark matter halo structure. So this can be things like galaxy formation efficiency across halo masses, can be baryonic feedback and how that modulates galaxy halo structure. And then you can also go out to even larger scales and think about galaxy halo assembly in a hierarchical universe. And so these are now things like interactions and environmental processes between galaxies and halos and hierarchical assembly across mass scales. So this kind of sets the picture of the general ideas that I'm thinking about. As I kind of mentioned in my introduction, dwarf galaxies have been a very promising probe for dark matter and for the nature of dark matter for a long time. But to really use these galaxies as precise probes of dark matter, especially on a population scale, we really need to understand this messy and complex baryonic physics that go into their formation as well. And really, this is a multi-scale, multi-physics problem, and constraining this multi-scale picture requires a holistic view of the dwarf population. One other thing that's been observationally difficult with dwarfs that's really changing or really set to change with this next generation of surveys is that dwarfs are low mass, so they're faint. So it's harder to see dwarfs out to larger distances. And a lot of our best information about these low mass galaxies comes from very nearby systems. And that can make generalization a little bit difficult because we are also sitting in the Milky Way, which may also be affecting the evolution of these dwarf galaxies. So we really want to reach out into the population scale, reach out to larger distances, and marginalize over environments in order to constrain this baryonic physics at different scales. So I work on different bins within these schematics. Today, because this is a relatively short talk, I want to focus just on two of these bins. So gas flows in the ISN and CGM and interactions and environmental processes. And before I really dive into the specific projects, I also want to take a second to talk about why I'm especially excited about population scales or population scale studies of dwarf galaxies now. So wide field surveys provide this multi-scale view of the galaxy population, which we're really looking to expand into the dwarf galaxy regime. But just stating that doesn't really answer the question of why we're interested or why we're so excited about getting down to lower masses now. And I'm going to give you a little bit of a visual representation of the timeline for wide field galaxy surveys as a function of galaxy mass. So here I'm not showing a dwarf galaxy. This is, an L star kind of Milky Way-like spiral. But from the left to the right, I'm showing the digitized sky survey. So this is like 1990s. The Sloan Digital Sky Survey, so SDSS, which ran from maybe like late 90s to almost 2010. And then at the right, I'm showing HSC, or the Hypersuprime Can Subaru Strategic Program, which ran from maybe 2014, 2015 to around 2022. And here you can see that even back in the 90s, we were able to say very detailed and quantitative things about the structure of these more massive galaxies. And of course, this isn't to say that, we solved massive galaxies in the 90s and there's nothing left to do with them. I think we're still uncovering a great deal about massive galaxies, especially in the kind of very high spatial resolution and very low surface brightness outskirts. But this is just to say that, even a few decades ago, we could say very quantitative things about the population of these more massive galaxies. But if I flip to a kind of more dwarfy galaxy, so this galaxy is around an SNC mass, it's around 10 to the 8 solar masses and stellar mass, the picture becomes very, very different. So these are the same surveys, but now at the left, you see that DSS, yes, it is a significant detection kind of in retrospect because you can see that the galaxy is there in the more recent surveys, but it really just looks like a little smudge. And then when we get to SCSS, we can start to resolve kind of global properties about the galaxy, maybe say something about its brightest star forming region, which you can see is that blue dot in like just left of center. But it's really only recently with the expansion of very deep and high resolution wide field imaging that we've been able to say detailed and quantitative things about dwarf galaxies at a population scale in the same way that we've been able to do at more massive galaxies. So now you can see not only a lot more star-forming regions, you can start to see into the outskirts of the dwarf galaxy, really get a more detailed look at its morphology. So today I'm going to be talking largely about two observational efforts. The first one is or I should say the first 50% of one, which will become more clear in a second, is the SAGA survey. So this is a spectroscopic survey about placing the Milky Way in cosmological context. We recently had our third data release, which is the spectroscopic confirmation of 378 satellites of 101 nearby Milky Way-like galaxies. But I should mention that to find these 378 main survey satellites, the team had to observe over 40,000 spectra in total over around a decade of observation. So this is an effective purity for the sample or for the survey of less than 1%. And I'm not going to have much time to talk about the Saga main survey, but I just want to drop a quick advertisement. So at the right, this is a postage stamps of all 378 satellites colored by host. And this allows you to really put the Milky Way satellite system in cosmological context and compare Milky Way satellites to cosmic analogs in things like star formation rates, spatial distribution, and quenching processes. So I said that what I was really interested in is population scale studies of dwarf galaxies. And although the Saga satellite sample is great, it's not really a population sample of all dwarf galaxies. In fact, it's a very specific selection of satellite dwarfs around Milky Way-like galaxies. And so what I'm actually going to be mostly talking about is the Saga background sample. So as I mentioned, the Saga sample purity is about 1%. But because of the photometric selection, the remaining 99% of spectra are mostly dwarfs at slightly higher redshift. They're selected to be pretty blue in their optical colors, pretty low surface brightness, and those kinds of selections will get you mostly low mass galaxies. The Saga background sample is also 3 times more sensitive than previous wide field spectroscopic efforts. So here I'm showing the distribution of the Saga background sample in blue over stellar mass and redshift. And in the red dashed line, I'm showing kind of the approximate limiting magnitude of gamma at 19.8, give you a sense of how we're pushing down to lower masses as a function of redshift. And the real challenge of working with the Saga background sample is that the observational selection function is complex, right? These galaxies are not selected for low redshift dwarfs necessarily. They're selected in the hope that they were satellite systems of foreground galaxy. But because the selection function is quantifiable, as long as you can quantify the selection function, you can also invert it to learn something about the underlying population. So now I'm going to jump into a couple science questions. First, I want to talk about star formation feedback, so kind of processes internal to the dwarf galaxies. We have the general picture that at dwarf mass scales, the main contributor to galaxy and baryonic formation modulation is stellar feedback and largely supernova that drive galactic winds. And these winds carry gas mass or energy out of the central galaxy. So here you can see a little schematic of a dwarf galaxy. Some supernova go off and they push galactic winds out of the midplane. This is relevant to Landesian problems like core cusp, like quiescent fractions of dwarfs, size diversity, and rotation curve diversity. So star formation drives outflows that carry mass and energy out of the galaxy. And you can think of this feedback in largely kind of 2 different bins. The first is ejective feedback, which suppresses star formation by removing gas from the system, by removing mass from the system. And then the second is preventative feedback, which suppresses star formation by rather injecting energy to prevent gas from cooling onto the galaxy. So either gas cooling back from the CGM or gas cooling from cosmic inflows onto the galaxy. The question, though, is which mode of feedback dominates? And this becomes more important because in simulations, it's been found that both strongly ejective and strongly preventative feedback schemes can create galaxies that are realistic in some ways. And so we really want an observational handle on this feedback in order to differentiate between two very plausible modes, at least in simulations. So the challenge is observing winds. So here's M82. And that's kind of our canonical poster child for galactic winds. One way to measure the strength particularly of ejective feedback, is via the mass loading factor. So this is just defined as the ratio between the mass outflow rate and the star formation rate. For cases like MAD2, it's a little bit easier because you can see the wind directly, but we can only directly observe these outflows for a few vigorous and nearby cases. And for kind of direct measurements of the mass loading factor, geometry can be a challenge because you're looking to find the mass outflow rate of something that's projected on the sky. So you can either, this is a bit of a hyperbole, but in the two limiting cases, you might see the galaxy edge on, so you know how high the gas has been lifted out of the galaxy, but you don't know how fast it's going, which is a problem if you want the rate. Or you might see it face on. So you know how fast the gas is going, but you don't know if it's actually out of the disk. But thankfully, the baryon cycle doesn't just move in heat material, and the production of elements heavier than helium is dominated by stellar processes. And specific elements like oxygen are dominated by processes in massive stars. So looping back to the saga background sample, I'm thinking about population scale samples of dwarfs. Mass loading, the mass loading factor can also be measured via differential chemical evolution modeling. So our approach is essentially to use our observed redshift zero galaxies as a boundary condition, making the statement that they must be realistic galaxies because they are in fact real galaxies. And then we use a simplified model to evolve these galaxies back in time. So what that looks like is taking something like the gas phase oxygen abundance and the stellar mass at redshift zero, using our redshift zero galaxies as our model boundary condition, and then taking our model galaxies and integrating their properties back to higher look-back times for some parameter set theta of our model, the mass loading factor being one of those parameters. And that will give us a prediction for what, for example, gas phase oxygen abundance and stellar mass looks like at higher redshift. If we know our Saga background selection function, we can then apply that selection function to the model and allow a direct comparison between our model predictions and our higher redshift observations to infer the probability of this parameter set given our data. So to give you a sense of what that looks like in practice, here I'm showing the stellar mass versus mass loading factor. The blue cross now is our inferred mass loading factor using this differential chemical evolution modeling. And I'm now going to show you what that looks like compared to some simulations. So I just overlaid a suite of different idealized galaxy simulations from the literature. So these are kind of high resolution, non-cosmological simulations that are really focused on ISM dynamics. And now you can also see, if I overlay a suite of cosmological simulations, that the mass loading factor that we measure is in line with idealized simulations, but substantially lower than what many cosmological simulations use to achieve otherwise very realistic populations of dwarfs. So in this mass range, we infer a mass loading factor of around 1. For the same mass range, many cosmological simulations use or derive mass loading factors of more like 10 to 30. And I should also note that our differential chemical evolution modeling approach also agrees with direct observations of mass loading from low mass dwarf galaxies. So this indicates that observations are really converging towards this low ejective feedback scheme. And I'll make a very quick side note that taken with a later measurement that we made of the stellar to halo mass relation with the Saga background sample, this overall picture of the sample prefers a high energy loading or preventative feedback scheme. So there I was really talking about processes that are internal to dwarf galaxies and how those modulate the cyclic movement of baryons in and out of their halos. But of course, dwarf galaxies are also not evolving in isolation. So I'm going to take the last little bit of this talk to really think about dwarf galaxies and their environments. So if we think about a dwarf galaxy and its ISM and its CGM, how that gas reservoir evolves in isolation is very different than when you introduce a massive galaxy. So when a dwarf galaxy falls into a host halo, we think that the massive galaxies generally either strip satellite gas or cut off gas supply. But in some, this leads to quenched satellite populations. So we see quenching very commonly around massive halos, but really uncommonly for isolated dwarfs. And understanding how dwarfs quench their star formation is very relevant for things like size diversity and how it plays into morphological transformation of dwarfs. Of course, it's very directly relevant to quiescent fractions of dwarf galaxies and also stellar to halo mass relation. So, as I mentioned indirectly, the presence of a massive host leads to quenched satellites. Uh, and here I'm showing quenched fraction versus stellar mass for the Milky Way and M31 in orange and the Saga survey in green. So the error bars here show the uncertainty on the mean quenched fraction across all hosts. The kind of solid green lines show the host-to-host scatter. So not the uncertainty on the mean quenched fraction, but how much the quenched fraction varies from one host to the other. And then in purple, I'm also showing SDSS isolated galaxies. So unlike the quenched satellites, where the quench fraction rises as a function of stellar mass, the SDSS galaxies, the quench fraction really plummets once you get down to dwarf masses. But SDSS is quite incomplete once you get down to these stellar masses. And to understand what the environmental effects of having the presence of the massive host really are, from a physical perspective, we really need to know the self-quenching efficiency of these dwarf galaxies. So just seeing that dwarfs are quenched around massive hosts isn't necessarily enough. We need to compare that to what their quench fraction would have been in isolation. So the Saga background sample is, again, a really great use case or a great way to probe these isolated systems because it's deeper than previous surveys and because it's really weighted towards these low mass galaxies. So here I'm showing a recent paper looking at the stellar mass function of the Saga background galaxies. It's a function of environment. Top is satellite dwarfs, middle is field dwarfs, the bottom is isolated dwarfs. And for this talk, we're just going to focus on the isolated dwarfs. So these are a subset of field dwarfs that are extremely isolated, more so than just what we would consider a central galaxy. If we look at the quenched fraction of these very isolated dwarfs, we see that observations and empirical modeling point to very low quenched fractions. So in orange, I'm showing universe machine, which is empirical modeling, which was itself based off of the Saga main sample, so not the Saga background sample, but a similar observational constraint. The green is the SDSS measurements, the Jiha et al. 2012. And then the blue, I'm showing updated measurements from the Saga background sample and gamma. So this shows that down to stellar masses of a few times 10 to the 8 solar masses, observations imply that really only around 1 in 1,000 isolated dwarfs are quenched. But if we then compare these results to cosmological simulations, we see quite a different story. So in cosmological simulations, there's a pretty common kind of turnover in the quenched fraction. So these are all either central or isolated galaxies. So the quenching should be largely internally driven or self-quenching. And each of these hatched or scatter or curves are shown in a different simulation. But you see that although the turnaround mass changes, almost all of these simulations predict some sort of turnaround to higher quenched fractions in the kind of SNC to LMC mass range. So this implies that cosmological simulations are over-predicting dwarfs' ability to quench in isolation. And this is especially important because I'm not saying that cosmological simulations are just getting everything wrong and they're predicting just completely unrealistic populations of dwarfs. A lot of these cosmological simulations are able to reproduce other metrics of the galaxy, low mass galaxy population extremely well. So in a recent paper, we also looked at the stellar to halo mass relation of dwarf galaxies, and all of the simulations that I'm showing here are able to reproduce the stellar to halo mass relation down through the Saga background mass range extremely well. So this is really pointing to the idea that baryonic processes in dwarf galaxies are extremely complex and kind of that you need a very high dimensional or very multi-pronged approach to really pin down when and where the physical prescriptions in these simulations are able to reproduce the observed galaxy population. And I'd also say that, moreover, some field dwarf quenching mechanisms are likely to be temporary. So there's a few kind of central or field or isolated quench dwarfs out in the literature. Here I'm showing one of my own papers, which I'm showing because there's a pretty obvious quenching mechanism for this particular sample or for this particular system, where we see that there's a quenched companion with H1 displaced in its tidal tails, and this starburst also dwarf companion with a very centrally concentrated H1 reservoir. And so the quenched companion appears to be quenched by the interaction with another low mass galaxy, with a time scale of star formation reignition of about a few hundred megayears. So really, even when observations show that field dwarf quenching is possible, some of these mechanisms are also probably temporary, so they're not necessarily contributing to the buildup of a quiescent dwarf galaxy population. And the reason why I bring up that last point is because for the last couple minutes of the talk, I'm going to touch very briefly on interactions between dwarf galaxies and how those shape the formation of these low mass systems. So other nearby dwarfs, as I just stated, are also expected to influence star formation, both in quenching and in triggering star formation. And this can have a lot of relevance for, again, different problems in lambda CDM, especially quiescent fractions again, but also stellar to halo mass relation and size diversity. So I said that individual cases show that dwarf-dwarf interactions can quench star formation. Spectroscopic studies also show that dwarf mergers are correlated with elevated star formation. So if you look for either interacting dwarfs or dwarfs in pairs, as you go up to higher H alpha equivalent widths or more vigorously star forming galaxies, you generally see that the merger fraction increases. One kind of problem with finding these dwarf pairs en masse, or these interacting dwarf galaxies en masse, is finding the dwarf galaxies themselves. So getting photometric or getting reliable redshifts, I should say, at these masses and redshift ranges remains challenging. So one thing that I want to briefly advertise is the Marian survey, which is dwarf finding en masse with emission line imaging. So here I'm showing the HSC, or some HSC cutout, I should say. And there are around 5 low mass galaxies with a redshift between 0.05 and 0.1 in this image. If you just look at the HSC broadband image, it is extremely difficult to pick out which of these galaxies they might be. But if you go to emission line imaging, so we have 2 medium bands, one that's centered on O3 and one that's centered on H alpha. If you just look at galaxies that emit in both of these medium bands, finding galaxies in this redshift range, at least star-forming line-emitting galaxies, becomes much easier. So now I'm overlaying both the O3 and the H alpha emission on the left and the right, and you can see that these 5 galaxies now pop out. Right. So here I'm just showing the transmission curves for our medium band filters. So again, we have one on O3, one on N708. The Marian survey is aiming to collect reliable redshifts for 100,000 dwarfs between redshifts of 0.06 to 0.1, with 2 main science pillars. The first is to map out star formation in a mass complete sample down to stellar masses around 10 to the 8 solar masses, so around SMC mass. And then the second is to measure the dark matter content of those dwarfs via weak lensing. And for both of those, getting this wide field of view where you get every dwarf that's in your field of view that's emitting is really important. And because I'm running out of time, I'm just going to give a really quick teaser for some preliminary work I've been excited about lately, which is probabilistic identification of low mass mergers at scale. Here I'm just showing at left some HSC broadband imaging, as well as a substructure image that we use to really pull out the merger features. The left is a very major merger. I don't think you need the substructure image to really tell that it's a merger, and there's a this big stream and shell structure coming off of it. But the right is a lot more subtle. You do see a stellar stream kind of in the southeast, um, but you really need the substructure to pull it out. And then at the right, I'm showing the distance above the main sequence, or sorry, the merger detection rate as a function of the distance above the star forming sequence. But this is all preliminary, so I just mean it as a teaser for the variant sample. I'm, of course, happy to talk about it later if anybody's interested. But there, I just want to wrap up with the statement that I've made several times throughout the talk and in my intro, which is that dwarfs are really powerful testing grounds for lambda CDM. But we really need to understand their baryonic processes to harness their full potential as precise probes of dark matter. Our picture of these multi-scale baryonic processes is highly incomplete, but wide field surveys like Saga Background, like Marion, and of course like LSST and Roman, all of these great next generation surveys that are coming out, are able to provide population level insights into these processes. And in my talk, I stated that dwarf winds are really only moderately mass loaded, mass loading factors of around 1, which is substantially lower than many adopted ejective schemes that, again, are able to create relatively realistic samples of dwarfs. Dwarf self-quenching remains highly inefficient near SMC masses, unlike turnaround prediction. And dwarf interactions can both trigger and quench star formation. Stay tuned for census scale results from Marion. And overall, this growing observational picture of a less violently ejective feedback cycle in low mass galaxies. Thank you.
Yay. Thank you for the super nice talk and actually leaving time at the end for discussion, which is great. Yes. So without further ado, let's open up the floor for questions. Anyone? I'm sure there should be plenty. Such a nice talk. I don't know, how do we do this? Feel free to just unmute and ask your question, it's fine. We have a small enough group for that. Benny, do you have questions?
Of course I do, but I sound terrible. So I do have one about the environment. So you have the background survey, which means that you didn't select for environment, but you do have an indication of environment. Where did you get that from? Is that from
Yeah,
Sloan or the local groups of Milky Way galaxies nearby or something like that?
yeah. So the environment comes from for the stellar mass functions in particular, for the stellar mass function work, we restricted down to redshift zero point 0.05 and used hosts from 2MASS. For the chemical evolution modeling, we use all dwarf galaxies regardless of environment, with the exception that we did not use the Saga survey satellites themselves. Because of course, if you select for only things that are in a Saga field, you're going to end up with an overabundance of very low redshift Milky Way like satellites.
Okay. And follow up on the Marian survey
Mhm.
is which fields are those? Is that deep fields or
Yeah, it's 600 square degrees in HSC equatorial fields. And that includes Cosmos and the XMM HSC
okay.
deep fields.
Okay. Thank you. That was just a thing I was interested in. I think I've seen the survey go by, but I hadn't looked at the paper in enough detail to remember that. So thank you. I need somebody else to ask a question before my voice completely goes out.
Jason, has you unmuted yourself?
Yeah. Um, so fantastic talk. I'm curious, do you see any difference between galaxies that are simply isolated and don't have a host versus ones that are out in voids where they're actually in very low density environments?
That's a great question. I haven't looked specifically at void galaxies. I think it would also be interesting on just to add to my own list of things to look at. I think it'd also be interesting to look at things in voids that are not necessarily super isolated from other dwarf galaxies, but are isolated from large scale structure versus things that are not in voids that are similarly around dwarf galaxies, but not very massive galaxies. So I think there is a kind of subtle distinction between the very large scale environment and like void versus filament and the very small scale environment of is it actively falling into a massive galaxy's halo? But that's a great question.
Yeah, it would be interesting to see how that plays out. Well, TBD then.
Yeah.
Any other questions from the room? I can ask a quick one. So you mentioned Roman very briefly at the very end. So any
Mhm.
plans or hope that Roman will help improve some of these measurements and imaging?
Yeah, so I think that there's this interesting observation, or there's this interesting divide in the observational dwarf galaxy community because there are some people that think specifically about resolved star dwarfs, and there are some people that think specifically about integrated light dwarfs. And of course, these dwarf systems are fundamentally the same type of galaxy, so we should be talking to each other. But practically speaking, a lot of the capabilities and the measurement methods that are used for integrated light versus resolved star are very different. And there's not much kind of cross testing between these methods to make sure that they arrive at the same physical result. Part of that is because I think of the sociological effect of these are slightly different communities, but part of it is that for some integrated light target, I mean, sorry, for some resolved star targets, they become so close that it's hard to make kind of reliable integrated light measurements in the same way. So I think one thing that I'm really excited about with Roman is its ability to push out to much larger distances with resolved stars. And I think that that will both kind of bolster the need to get these two communities on the same page, and give more leverage to actually put these methods and put these measurements on equal footing.
Awesome. Benny, go for it.
Risking my voice here, but I saw that the gas reservoir, so the H1 reservoir, is kind of key what you found in that one individual pair
Mm-hmm,
of dwarfs.
mm-hmm.
So would you say that if you get the gas, what does the gas reservoir actually say about the feedback? Or is it just a like, well, it must have run out recently, or is it
Yeah,
more of a morphology?
yeah, I think in that specific case, so if you looked at the galaxy with just single dish H1, you would think that it would have a very massive H1 reservoir. And it seems to be that the H1 reservoir in that particular interaction was pulled out from one galaxy, but not the other. I think that it's still a little bit unclear why there's such a strong asymmetry because their stellar masses are nearly 1 to 1. So it's a pretty equal mass merger. So it's not quite clear why one galaxy is so effectively able to hang on to its gas reservoir, and the other is totally cleared out of the center. I think with just one case, it's hard to say how much of this is kind of a common occurrence in dwarf-dwarf pairs versus this very special kind of orbit configuration and catching it at a special time. And so I think that expanding our view of dwarf pairs and low mass mergers will really be key in understanding how prevalent this mechanism actually is.
Okay, because we're going into the era of large all-sky H1 surveys that are
Right.
actually interferometric, so you can actually get resolution. And
Yeah.
so I was curious if just the H1 content would tell you something, but you need the configuration, where it is in the galaxy as well.
Yeah, I think that just having the H1 will tell you something interesting if you see that there's this galaxy that for some reason has a ton of H1 but no star formation. I think it's a definite flag to follow up. But I think the configuration is really key to demonstrating that it's uh, kind of tidal in nature. But I think just showing so if you imagine that you can get H1 for all of these low mass galaxies, but you don't have any spatial resolution. Um, I think that if you saw a prevalent kind of correlation between suppressed star formation despite a lot of gas and being near another dwarf galaxy, that would give you a very strong lead that tidal interactions are key in kind of temporarily suppressing star formation in otherwise isolated dwarfs, even if you don't necessarily see the tidal features in every individual system.
I'm just going to follow up before the voice gives out completely. You would expect two star formation indicators, for example, to be. So if you look at stochasticity in these galaxies,
Yeah.
right, these things wobble up and down in all kinds of simulations, but we don't have a
Hmm.
good observational grip on that.
Yeah.
So you'd expect that to be, a very steep gradient between, let's say, the UV derived and the H alpha derived star formation rates, right? Is that
Yeah, exactly. Actually, one of the reasons why that particular pair was picked out originally is that it's quite bright in UV, and you can even see it has a lot of young star clusters, but no H alpha emission at all. So the H alpha to UV ratio is the first thing that flagged it as kind of an odd system.
okay? Oh, fantastic. Thank you.
Yeah, this discussion gives me a lot of flashback undergraduate days with the Alpha Alpha team when they found this H1 rich galaxy with like almost no star formation.
Yeah.
Yeah, cool. Any other questions from the room?
Oh, yeah, can I just ask?
Yes, go for it.
Oh, yeah. I'm a high school student and I'm really interested in this area. So thank you for your talk. But I was wondering, to my understanding, the Saga survey uses like a set assumed projected value for the or not a set value for the virial radius at 300 kiloparsecs.
Mhm.
So I guess this is kind of two things. Um, is there like in terms of differentiating between bound satellites and like backsplash objects that have been recently ejected from the system, um, is there a kind of like is there not really like a clear determination between what's being considered a satellite versus an isolated galaxy in that sense? And also is there any relevance of these galaxies that might be just beyond the virial radius and have just kind of escapes the system and determining the quench fraction?
Yeah. So let me answer your question in parts. So first, there is when we assign something as a satellite or not a satellite of the Saga host, we're using the observed redshift. It tells us the velocity difference between the satellite galaxy and the host. So there is some uncertainty in exactly when a satellite is bound versus when it's not. In terms of the Saga background sample, though, because if you think about observing a fixed area on the sky as a function of distance, because the Saga hosts are very close to us and the Saga background sample extends out to higher redshift, the potential kind of mislabeled satellites, which we don't think there are many of in the Saga survey, but because of the distance and volume scaling, any sort of galaxies that are very close to the Saga host account for an extremely small fraction of the volume compared to the background galaxies in the background volume that's probed by the Saga background sample. And that's just because if you're thinking about like viewing something through a sphere, when you're very close, you have a very small area, and then it increases as you go out. So we don't think that it's a really big contributor either for the Saga survey itself or the Saga background sample. And then for your question about the fixed virial radius, again, for the Saga background sample, it's essentially, you can think about it as instead of taking fields of a fixed size in square degrees, let's say, or a fixed number of telescope pointings, we just have this funny area definition where the fields are as large as the 300 kiloparsecs for some host in the foreground.
Okay, thank you.
Great. Any other questions from the room? Going one, going twice. All right, I'll make a final announcement. So thank you, Erin, for joining us today and giving this nice talk. We will continue to have these monthly seminars scheduled for the first Wednesday of the month for the rest of the academic year. we have March 4th that is up for grabs, and as well as all the third Wednesday of the week of the month. So if there's interesting results, timely results, or a paper that you're about to put out and want to use this platform to share with the rest of the Galaxy Science Interest Group, feel free to reach out to me and Benny, and we'll put you into the schedule. Yeah, let's thank Erin again, and we'll see you again in a month. Yay.
Thank you.
Thank you. Bye, everyone. All right, let me